Hello everyone. Today we are here again for part 2 in finite element method. Quick summary of the part 1 lecture series. In last lecture we have discussed about the basic steps for solving any problem using finite element method. It may be structural or it may be fluid problem or it may be heat transfer problems. Now there are 2 or 3 basic issues which especially the UG student they regularly face, especially while assembling the global stiffness matrix or forming the global stiffness matrix, and secondary while applying the boundary condition. May it be the structural issues or may it be the thermal issues. In today's part 2 lecture, I am going to cover how to formulate the global stiffness matrix for a given problem, especially the structural problem. Before coming to that, the structure problem basically covers 3 domains: bar, beam and truss. These are some types of problems which you can come across while exploring the syllabus. In bar problem, you will be having 2 types of issues. One is bar having uniform cross section, and second is bar having reducing or increasing cross section. In beam problem, there would be 2 kinds of problem. One is where load is just acting on a node or load is only point. In second case, load is not point but it's in another type like UDL or UBL. In truss problem, you will be having simple plain truss. It means x or y dimension. You need to specify the various parameters and solve this problem. So today, to explain the formation of global stiffness matrix, I have taken a beam problem with case 1. This is the problem. We have a cantilever, not cantilever beam, simple beam of 10 meter. It has at a center load of 2000 kilonewton, not 2000 kilonewton but 200 kilonewton. The modulus of elasticity is 20 into 10 power 6 kilonewton per meter power 4, then your I. Now to solve this problem, firstly I need to follow step number 1. In last lecture we have already covered step number 1 called discretization of your whole problem into small element and configuration of that. So here I have configured because we are using one dimensional problem for solving the beam problem, so I have modeled this beam into using simple one dimensional bar problem. So this is our simple bar. We have firstly noted the numbering of the elements because there is a point load, and we have also we are seeing that there is a discretization between the elemental length. So here at this point of time we need to specify a single node, because to apply the load at a particular point we need to specify the node at that particular point, because if we are not going to specify any node, then finite element problem or finite element method is not going to take the effect of this particular load. So that's why we have considered point number 2 over here and point number 3 over here. It means element 1, element 2, then node numbering element node number 1, node number 2, node number 3. Here at node number 3 also we are having roller support. Okay, you know the K1 and K2, how to form the local stiffness matrix. There are already ready-made formulas. You need to just pick those formula. I have already written the K1 and K2 matrix. Now to assemble K1 and K2 into global sense, we need to figure it out, the numbering of local stiffness matrix K1 and K2, and then numbering of global stiffness matrix, and then how to connect K1 and K2 with global stiffness matrix. So in first step, the numbering of K1. K1 means the stiffness matrix for element number 1. Okay, as we all know that for beam problem at a particular node there are 2 degrees of freedom. One is your vertical displacement and one is rotation term. It means V and theta at each node. If I am going to take element number 1, this is element number 1, I have node 1, node 2, then V1, theta 1, then V2 and theta 2 here. In the same way, because K1 signify the element number 1. So that is why I am numbering B1, theta 1, B2, theta 2, again B1, theta 1, B2, theta 2. In the same way for stiffness matrix 2, because it is representing element number 2, so I am going to number accordingly. For element number 2, this element number 2, I have again rotation term and vertical displacement V. Now I am going to number. How to number for second element? Because for second element initial node is 2 and final node is 3. So here V2 theta 2, then V3 theta 3. 2 for initial node for element 2 and 3 for initial last node for element number 2. In the same way I am going to number V2 theta 2, B3 theta 3, V2 theta 2, B3 theta 3. Okay, K1 and K2 we have already formulated. Now I am going to assemble these. The basic formula for assembling is K global is equal to K1 plus K2. Now because I am using K1 and K2 matrix for Kg or K global, initially I need to specify the dimension of stiffness matrix. One property we already know, that stiffness matrix is always going to be symmetric. Okay, the local stiffness matrix size of this is 4 cross 4, then for K2 4 cross 4 again. To determine the global stiffness matrix size, there is a specific formula. K size will be equal to total number of node in a particular problem into degree of freedom per node. Here we are having how many number of node? Node 1, 2, 3. It means 3 into, because it's beam problem. In beam at every single node there are 2 degree of freedom. One is displacement, vertical displacement, and one is rotation term. Because in beam we are going to apply the transverse load. Transverse load means like perpendicular to your normal x-axis. In that case, to know the exact shape of this beam, initially this vertical term or vertical displacement is going to displace from this location to this location based on application of load. But to get the exact shape of the beam or deformed beam, we need to have information about this rotation term. That is why in beam problem every node has one displacement, vertical displacement term, and second is rotation term. So total number of node 3 into number of degree of freedom per node 2. One is displacement and one is rotation. It means 6. Our size will be 6 cross 6. If size is going to be 6 cross 6, in the same way we are going to specify the various numbers. How we are going to specify the numbers? Number are very straightforward. V1 theta 1, V2 theta 2, V3 theta 3, then again V1 theta 1, V2 theta 2, V3 theta 3. You can also see that there are 3 number of node. It means for node 1 these are 2 degree of freedom for node 1. Okay. For node 2 these are the terms. Node 3 these are the terms. Node 1, node 2 and node 3. Okay. Now how to proceed from K1, K2 to K global? Basically our objective is to fill this matrix with the help of K1 and K2. The very simplest way is to export each and every element from K1 matrix to this. In the similar way, export each and every element of K2 matrix and grab it over here. Okay. One thing very common is that because in K1 and K2 we are having same constant 4800 by 125, 4800 by 125. The basic property is that if anything is common in this particular matrix, it means that this term is multiplied by each and every term. Because for K1 and K2 this is common, so we are going to take the same value as a common. So it's 4800 by 125. Now you need to focus, because here a small mistakes in numbering or find out the location of a particular element of a matrix, that is going to say distort your stiffness matrix. If your stiffness matrix is not correct, then your whole problem is going to be wrong. So how I am going to cover it? Firstly, locate the point number 1. The point number 1, it means it is located at V1 column and V1 row. Now again map V1 to global matrix. This is V1 row, V1 column. It means value is 12. I have put 12. Then theta 1 second column first row. This is 30. Then again theta 2 V1 minus 12, theta 2 V1, it is 30. In the similar way, 30, 100 minus 30, 30, 100 minus 30, 50. Then for V2, again this is V2, initial term is 12, then theta 1 V2, that term is minus 30, then 12, then minus 30. Okay. Fourth is minus 30, not 50, minus 30, so make it more clear, minus 30, this is 100. This is the contribution of stiffness matrix K1 on the global stiffness matrix. Now in similar way, stiffness matrix K2 into global stiffness matrix. So firstly locate this particular point. Location is column number V2 and row number V2. So we are having V1 theta 1 V2 theta 2. So this is row number V2 and column number V2. We are already having a value from the stiffness matrix 1. If we are having again a same value on that particular point, so we are going to either add it or subtract it based on the convention or sign we are having. So its location is V2 column and V2 row. V2 row, V2 column. So 12, here value is plus 12. Initial value was minus 12, not this. Okay. Now in second element is your theta 2, column number theta 2, then row number V2 again. So we are having 30, minus 30 initial, this is plus 30, then column number V3 and row number V2. So column number V3 and row number V2, value is minus 12, then column number theta 3 V2, theta 3 V2, value is minus 30. Okay. For second row, the it means Q2, first element is 30, location is row number Q2, column number V2. So column number V2 is here, row number theta 2 is here. So value is minus 30 was the initial, this is plus 30. Then for second element theta 2, column theta 2, row theta 2, 100 plus 100, then rest values are minus 30 and then 50. Third element theta 2 and theta 3, column number V2 this and theta 3, sorry beta 3. So minus 12, next value will be minus 30, then V3 and V3, the value is 12 minus 30. For last element the value would be 30, 50, then minus 30 and 100. This is the contribution of stiffness matrix K2. Now to make it more precise, here we are having 100 plus 100, 200 plus minus 30, it's going to be 0, plus minus 30, it is going to be 0, and plus minus, this was, sorry, 12 plus 12 is 24. Now, these four elements, V1 theta 1, V2 theta 2 till here, they were the contribution for element stiffness matrix K1, and these were the contribution for element stiffness matrix K2. You see, these four values has been changed. Why these four values changed? Because here node number 2 is common for element 1 and for element number 2. That is why for beta 2 and theta 2, it means these values, beta 2, theta 2 in column and beta 2 and theta 2 in row, we would be having their contribution, one from stiffness matrix K1 and one from K2. Now there are, you see there are many elements where we do not have any specific value. For that case, you are going to put simple 0, simple zeros. Now how to check that whether my stiffness matrix is correct or not? There is specific property that this is stiffness matrix is square, and if you draw the diagonal, then it should be symmetric about this. It means this is your diagonal plus here 30, 30, minus 30, minus 30, this 0 over here 0, minus 30, minus 30, minus 30, minus 30, then this is 0, 0, 30. This is very effective way to check whether you are making it right or wrong, because if your stiffness matrix is wrong, it means you are not considering a particular node value or their distribution. In that case, the whole problem in the sense the numerical solution of that particular problem is going to be changed. So after formulation of stiffness matrix, you need to specify the cross diagonal and then check whether the upper triangular matrix is exact mirror of lower triangular matrix or not. If it is correct, then that's called. This is part 2 in summary. To formulate the global stiffness matrix, you need to calculate K1, K2, then find out the space size of stiffness matrix. Formula is total number of node into degree of freedom. Node is 3, degree of freedom is 2 because every term theta V1, theta 1. Displacement or rotation, 3 into 2 is equal to 6. Our size is 6 of 6. Again V1 theta 1, V2 theta 2. In this way you are going to write. Then export each and every element from K1 and import into K2. Then do some arithmetic. The space which are unfilled, you just simply put 0 over there to check the answers. Make cross diagonal, then check whether every element on the upper of that diagonal is reflected back or not. If it is reflected, it means your stiffness matrix is correct. Now in part 3 we will be covering how to apply the boundary conditions. Thank you.